Hello.
अस्सलाम वालेकुम मैम।
वालेकुम सलाम तहरीन, क्या हाल है?
मैं ठीक हूँ मैम, आप कैसी हैं?
मैं भी ठीक हूँ। हेलो शजील। हेलो।
Hi, yes, ma'am.
क्या हाल है?
How are you, ma'am?
आई एम फाइन, हाउ आर यू?
I'm बिल्कुल ठीक, आप कैसे हैं?
ठीक ठाक।
I'm good.
ओके, तो कैसा जा रहा है ऑनलाइन?
Till now, मैम अभी तक तो अच्छा ही जा रहा है।
अच्छा जा रहा है, गुड, दैट्स ग्रेट।
Yes, ma'am.
ओके, असद इज हियर।
Good
हेलो
afternoon,
असद।
ma'am. Hello, ma'am. How are you doing?
आई एम फाइन, हाउ आर यू?
I'm also doing fine. Thank you.
दैट्स ग्रेट। सो हाउस योर ऑनलाइन क्लासेस गोइंग?
Not bad, to be honest.
या, ओके, या,
Like, I thought that it won't be that good, but I'm enjoying learning online.
या। नो,
Perhaps because the courses are fun.
या,
Yeah, that's why. Just because the courses are fun, that's why I am enjoying learning
that's great.
online.
I'm happy to hear that. Okay, because I also, the positive side of it is the fact that, you felt a little bit left out when we were having the odd roll numbers, right? And you were not able to come. But
Yes, ma'am.
yeah, the positive side in this case is that everyone is being taught in the same way on at the same time, and you all have equal access, right?
Yes, ma'am.
So nobody feels left out or something like that, right?
Yes, ma'am. True that.
Mm. Okay, so we have two students missing, Durdana and Aman. Does anybody know anything about them?
Not from my side.
Okay, does anyone have contact? Ramin?
मैम मैं इमन से कहती हूँ।
दुर्दाना से भी कहो।
ओके मैम।
Okay, we can start. We were talking about Q value of a nuclear reaction the last time. So the main topic now is nuclear reactions. Okay, Durdana is here. And okay. And Raymond is also here. Good, great. So now we are complete. Okay, so we are studying nuclear reactions from Kaplan, okay? And the topic today is the Q value of a nuclear reaction. So let's just write it like that. So Q value of nuclear reaction. Okay, so in this case, like we said last time, this is also called the nuclear reaction energy. It's also called the nuclear disintegration energy. It's also called the energy balance of the reaction. So the standard equation that we write for such a reaction, as we know, is X, which is the incident particle, and it's incident on a nucleus, which is capital X, and you get a product which is capital Y, then a nucleus again, and small y, which is a product, plus there's a certain amount of energy that may be released. Okay, so this is called the Q value of the reaction. So this energy can either be absorbed or it may be released. So it's possible that Q can be positive. This means that Q is greater than 0, or Q can be negative. This means that Q is less than 0. So we know that this is, if it's positive and Q is greater than 0, then this is called an exothermic reaction, or it's called an exergic reaction. So exothermic. So heat is being produced. And in the second case, this is called endothermic. In this case, energy is absorbed by the reaction. So we know that for starting some reactions, we do need energy. Now I'm going to erase this, okay? Or I can start a derivation for this Q value, okay? In this case, we can consider this equation to be equation number, let's say 1. So x plus x will give you y plus y. So this is equation number 1. So let us assume that x is initially at rest, so that its kinetic energy is 0. If it's initially at rest, this is an assumption, then the kinetic energy will be equal to 0. And since the total energy of a particle or atom is the sum of the rest energy and the kinetic energy, the statement that the total energy is conserved is in the nuclear reaction means that, so by conservation of energy, we can say by conservation of energy, we can say that Ex plus mx c squared, okay, so will be equal to, this is for the incident particle, the small x. Then we have for the target nucleus, we have capital M and c squared. So small m is for the incident one, capital M is for the target one, and it is at rest, and therefore we don't have this term. E in this case represents kinetic energy. Okay, E's are the, capital E is the kinetic energy. And like I told you before, every book is using its own symbols, and therefore we have to understand and follow those symbols. And we should always define them when we are using them. So this is again a sum of the rest mass energy and the kinetic energy of the product plus of the particle, that is emitted particle, right? So this is small y and capital Y. Again, when you write this, be clear about how you write your small y and how you write your capital Y. So this will be equation number 2. Okay. Now we can introduce the quantity Q, which represents the difference between the kinetic energy of the products of the reaction and that of the incident particles. So therefore, we can say that Q is equal to E of the product nucleus plus E of the emitted particle minus E of the incident particle. So this can be equation number 3. So using equation 2, the quantity on the right hand side of equation number 3 can be expressed as in terms of the masses. So we're using equation 2 to write the right hand side of the equation number 3. So this will be, we can say that E y plus E small y minus Ex will be equal to in terms of the masses of these particles. So this is capital X plus small x minus m capital Y minus m. So it's a difference, small y, and whole multiplied by c squared. So this is equation number 4. So comparing these equations, three and 4, we have the value of Q as E capital Y plus E small y minus Ex. This is equal to the mass differences that we just wrote. So we can calculate them both in terms of the energies and in terms of the masses. So this is 4, this is 5. Okay. Now can I erase the board?
Sure, ma'am.
Okay.
Delete. Okay. Right. So now we can talk about the threshold energy. So in this case, we can define the threshold energy as the amount of energy needed for an endoergic reaction. Or we can say it is defined as the minimum amount of kinetic energy imparted to the incident particle to start a reaction. Again, as you remember that in order to start a reaction, you know that we need to impart energy many times. Like for example, in order to start a reaction, we sometimes heat, the substance, and heating means we are imparting energy. And so this energy will be in the form of the kinetic energy of the particle that is being bombarded. So the small x that we were talking about in the last case. So again, I define the threshold energy as the energy needed for a endoergic reaction or endothermic reaction, or it is defined as the minimum amount of kinetic energy imparted to the incident particle to start the reaction. So let us assume that we have a compound nucleus. Okay, so I will explain what is a compound nucleus. So in some reactions, you have a step in which a compound nucleus is formed. Okay, so for example, you can have N714, which is nitrogen, plus helium He24 will give a compound nucleus, which is an intermediate state, let's say, and which then later on breaks down into a product nucleus. And it emits a particle, which in this case is hydrogen 1, and hydrogen 1 we know is proton, right? Okay, and helium is a alpha particle. So if we want to speak in terms of particles, so the general equation for such a reaction can be written as, okay, in some books you have the small x first and the capital X second, and then sometimes they write the capital X, but you always know that it's the particle, small particle that's bombarded on the target nucleus, right? And then this intermediate step will be the compound nucleus, and then this is giving you a product nucleus and a product particle along with energy which may be positive or negative. So in such an endothermic reaction, the energy minus Q is needed to excite the compound nucleus sufficiently so that it will break up. So this compound nucleus is a nucleus which is in an unstable state, and this energy that Q we give to this reaction is the amount of energy that's required in order to excite this nucleus enough so that it will break apart and produce Y and small y. So this energy must be supplied in the form of kinetic energy of the incoming particle, and will then be available for excitation because some of it is used to impart momentum to the compound nucleus. So as you know that when we are bombarding particles, it's also moving. So there's a certain momentum also involved. This momentum is then distributed among the products of the reaction. So consequently, we can say that minus Q to be available for excitation of the compound nucleus, we must supply some energy in addition to minus Q. So it has the energy we need in order to excite this compound nucleus should be more than minus Q, because we need this step to take place and then we need to excite the compound nucleus. And this energy is then known as the threshold energy. Okay, so the energy which we have to provide in addition to minus Q so that we can excite this compound nucleus is then known as the threshold energy. Okay, and we can calculate this threshold energy using this equation where we have the momentum of the incident particle should be equal to the momentum of the compound nucleus, and from here we can then calculate the velocity of this particle, which will be in terms of the ratio of their masses multiplied by the initial velocity of the incident particle. So the part of the kinetic energy of the incident particle needed for excitation of the compound nucleus is then equal to minus Q is equal to half mx Vx squared minus half mc Vc squared. Okay, and we also know that mc is equal to mx plus m small x, and therefore minus Q will be equal to half mx Vx squared into mx divided by mx plus small mx. So therefore we can say that E threshold will be equal to half mx Vx squared, and therefore this is equal to minus Q into 1 plus mx over m capital X, because we have used the assumption that this ratio mx over M capital X is approximately equal to the ratios of their atomic numbers. So if we use these assumptions, then we can calculate this. Okay. Can I erase the board now?
Sure, ma'am.
Yes,
Okay.
ma'am.
Good. So we can erase this. Okay. Now we can speak a little bit about the compound nucleus. Now, this is a concept that was proposed by Bohr, and it has been useful in the correlation and the interpretation of nuclear reactions. So, Bohr assumed that a nuclear reaction takes place in two steps. So, the first step, he said, was the formation of the compound nucleus. So, according to this, the incident particle is absorbed by the initial or target nucleus to form a compound nucleus. The compound nucleus is formed due to the strong interaction between the incident particle and target nucleus. When particle reaches near target, Coulomb force vanishes and strong nuclear force comes into action, and energy of the incident particle is the induced energy. So for the first step, we have this incident particle coming to the target nucleus and exciting it in order to form a compound nucleus, which is sometimes represented by C with a star, or sometimes it's represented by C with a subscript N. So initial particle plus this can be called an initial nucleus or a target nucleus will give us a compound nucleus. So according to Bohr, the second step of the reaction would be the breakup of the compound nucleus. So according to his theory, the breakup of the second step after the formation of the compound nucleus would be the breakup of the compound nucleus. So sometimes you can also write it as C and N, or it's also called disintegration of CN. So the compound nucleus formed after a time, let's say, of 10 raised to minus 14 seconds or 10 raised to minus 15 seconds. So it's a very short time because it's unstable. So then it splits up or disintegrates by ejecting a particle, which can be the small y. It can be the ejection of a particle like a proton, a neutron, an alpha, etc., as we discussed in the beginning of these reactions, right? So Bohr assumes that the two steps, that is mode of disintegration of the compound nucleus, is independent of its mode of formation. So it depends on the properties of the compound nucleus, such as energy, angular momentum, and parity. So that was one concept that we used. Another concept that we use is called nuclear time. So this is the time required for a particle to travel across the nucleus, and it's known as the natural nuclear time. So we can write this, the time required for a particle to travel across the nucleus. And it's also known as the natural nuclear time. Okay. So can we erase the board now?
Yes,
Yes,
ma'am.
ma'am.
Good.
Yes, ma'am.
Okay. So another thing that we have been talking about is the binding energy, which plays an important role in these reactions. So we can talk about it. The binding energy that I was writing as BE, sometimes as it's also written as EB, and sometimes it's also written as I think B in your book also, right? Anyway, so the mass of a nucleus is slightly less than the mass of its constituent protons and neutrons. That's the basic concept. So in this case, the mass of the nucleus itself is less than the mass of the sum of the masses of the neutrons and the protons. So by Einstein's law of conservation of mass and energy, which is E is equal to mc squared, we know that this mass difference is equivalent to the energy released when the nucleons bind together. And if you calculate this, it comes out to be even a very small mass difference in atomic mass units, as we saw, uh, comes out to be a huge amount of energy. So therefore, this comes out to be sometimes in MeV, as you know, mega electron volts. So this energy is the binding energy, and it can be written by the simple formula. We can, depends on the problem that you have, and you have to decide whether you're going to use the simple binding energy formula or you have to use the empirical, semi-empirical binding energy formula. So this is another concept that comes in this topic. Another concept that we come across is called resonance. Now this resonance is different than the resonance that you've been studying in normal general physics. You remember the normal resonance that you studied?
Yes, ma'am.
So what is that?
When two beats, for example, if you were walking somewhere
Yeah.
and the natural frequency of that object is equivalent to the frequency of you inducing it upon that particular object, then it'll start vibrating with this frequency as well.
With the same
So
frequency.
given conditions are ideal, then its amplitude might just explode to infinity as well.
Its
But in real
amplitude
sources, there are
increases.
several
Yes.
constraints that keep it from.
Yeah. Okay. Anyway, we are now going to define this concept in the context of nuclear physics, which is different. Okay. So in this case, just as I told you, some terms are different, like cross section. We will be talking about that cross section, what it means in normal language or in normal general physics labs that we do, but then what it means when we come to nuclear physics. So in this case, the resonance is the reaction rate is maximum. We are talking about this in context of nuclear reactions. So it is maximum at particular energies. So this phenomena of occurrence of maxima in the reaction rate at different energies is called resonance. So the particular energies at which the maxima occurs are called resonances. So it can be used as in both ways. The particular energies at which the maxima occur are called resonances. Okay, so I can repeat this. The rate is maximum at particular, the rate of the reaction, right? The rate is maximum, or we can say the reaction rate. Let me write it here. The reaction rate is maximum at particular energies. You know that, okay, there's an announcement I have to make. My meeting will end after a few minutes, as you know, the Zoom does this, but then you just click the same link that I sent you before and you can enter the meeting again. Is that clear?
Sure,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay, great. So it will take a few minutes. I have like 9 minutes more, and after that you click the same link and then you can rejoin me in the meeting. Okay. So the reaction rate is maximum at particular energies. We know that a nuclear reaction depends upon the energy of the particle, right? Like we were talking about the fact, like for example, we will talk about this, for example, like a standard reaction like fission, for example, the incident particle has to have certain energy before it can start the reaction. So we need particular energies to start a reaction, and then the rate depends upon this. This phenomena of occurrence of maxima in the reaction rate at different energies is called resonance. And the particular energies at which the maxima occur are called resonances. So we can show this with the help of a diagram. Okay, so for example, you can see many graphs in many books. I'm just going to draw a rough graph just to illustrate the concept. Okay, so my graph will not be very correct. I mean, if you want to look at the values, you can go to a book and look at an actual graph. So for example, if we have, let's say, a reaction represented with a graph in which we have the kinetic energy of incident particle on the x-axis. Particle. And then you have the yield, which is the number of particles emitted per second. So let us consider an example of a reaction. Let's say an alpha P reaction. So alpha P reaction means the incident particle is a alpha particle, the product particle is a proton. And then there's an we can write it as aluminium, which is the incident, the target nucleus, capital X, and then alpha P, and we have the target, the product nucleus, which is silicon 30. So the incident particle in this case will be alpha, and the yield will be defined in terms of the particles emitted, which are in this case number of protons emitted per second. So this is the yield. Now you will see the graph will be such that, now my graph is really very hand-drawn. You have to go to a real graph in order to, if you want to really know these values. Anyway, you will see that there will be certain peaks at certain energy levels. You will see there will be certain peaks, okay? And these peaks, for example, will be called the resonances. This is the concept that we are explaining. So for example, for this particular reaction, if you check it up in a book, you will see that the alpha particle energies corresponding to the peaks which we are calling the resonances, are 4.0, 4. You can find these values in many different books and tables and so on. People have measured and calculated these energies and drawn these graphs. And these energies are in MeV. So this explains the concept of resonance. Also, like you know that I have been uploading videos on YouTube, so you can subscribe to YouTube so that whenever I upload a video, you will know about that. Okay?
Okay, ma'am.
Right. And now
Ma'am, can you please send the link to your YouTube channel on the WhatsApp group?
Okay, I'll check it. I'll check it. What's the link? I've been sending you links of individual videos in the beginning, but then I found that it was too time consuming to do that, right? So now I just want you to directly know when I upload a video. So some students have told me that they've seen it like that. I don't know if you need a link to see that.
When
Okay,
we
ma'am,
go to
I'll ask
Moodle,
some students if
Yeah,
they
I
if
think
they
you
have the
should be
access
able
to
to see
that.
it without a link. You know, what I was doing initially was I was posting you a separate link for every video, and that was very time consuming. So now, so that we save time and you immediately know when I upload it. So maybe I think you can access it without a link because I am not restricting them anymore. Okay? Is it?
Okay, ma'am.
okay, ma'am.
Okay, good. So now there's another concept we can talk about, and let me erase this. So this is the concept that we call the quasi-stationary state. Okay, so the natural nuclear time, which we said is the time required for a particle to travel across the nucleus, according to the compound nucleus theory, right, is of the order of very small, 10 raised to, let's say, minus 21 seconds. So the lifetime of a compound nucleus is about 10 raised to minus 15 seconds. So this interval is relatively long if you compare these two. So during this relatively long lifetime, the compound nucleus may be said to exist in a state of quasi-stationary state. Okay, the state between these two times is known as a quasi-stationary state. This means that through the although the lifetime of the nucleus is long, it can still disintegrate by ejecting one or more nucleons or by emitting gamma rays. So quasi-stationary states are known as virtual states or levels when the compound nucleus disintegrates by emitting one or more nucleons. So if the disintegration or the decay takes place by the emission of gamma rays, the compound nucleus is said to be in a bound state or in a bound level. Okay, so this was the concept of the quasi-stationary state. Now I think I will end the meeting so that we can then start a new topic. Okay, just click on the link you have.
Okay, ma'am.
Okay, ma'am.
Okay, ma'am.